All right, let's do it. We're gonna be doing LeetCode Biweekly contest 131. Hello, hi Pix. Hello, the zombie killer whale. Welcome to the stream. Congrats on your results, whale. Very impressive. Let's get started with Q1. Okay, Q1. Find the XOR of numbers which appear. You're given an array nums where each number in the array appears either once or twice. Return the bitwise XOR of all the numbers that appear twice in the array, or 0 if no number appears twice. Okay, and this one is the Q1. Usually it's an easy. Well, it is an easy here, and the size is pretty small, only up to 50 elements, and even the values are small, between 1 and 50. And we have the guarantee that each element occurs either once or twice. So we don't have to be clever about this. So one way to solve this, hey, smart coder, welcome to the stream. So one way to solve this is just to compute what we're told without thinking about any properties of the XOR or anything. So we care about the number of occurrences, so we could use a counter, right? So we could use a counter, and we want to filter the elements that occur 2 times, exactly 2 times, and then we want to XOR them. So we can use the reduce function for that with the XOR, and here we have a generator, and if the default value, the initial value is 0, so this should work. It's a one-liner. Cool. So this is a solution. So yeah, notice that it's kind of odd that usually with the XOR, when you do an XOR of many elements, the ones that occur 2 times will be canceled out, and the ones that occur 1 time won't be canceled out. But here we're asked for the opposite, the ones that occur 2 times. So well, here notice that this solution doesn't use any, well, like I said, here we could replace any binary operator, and any this 2 also, it's arbitrary. It could be any condition on the counts. So, but yeah, remember that for the 2 properties that you need to know for the XOR of X, the bitwise XOR of X and X is 0, and the XOR is X. Okay, so when you know these properties, so if you have X XORed 3 times, so these 2 are going to be equal 0 because of what we have here, and then you have 0 XOR X, which is X. And this pattern generalizes. It's what I said, that if you have X an odd number of times, it's going to be the XOR of all of them is going to be X. But if it's an even number of times, it's going to be 0. Okay, and why do we care about this? Well, So maybe we can, if we add one element, one occurrence of each element, we could change the number of occurrences so that the ones that occur once will occur twice, which are the ones that are gonna be canceled out, and the ones that appear twice will appear 3 times, which is the ones that won't be canceled out. Is the same as so occurring 3 times is the same as occurring 1 time. So a different solution of this would be to get the unique elements and add 1 occurrence for each unique element, and that should also work. Right. So now we are using the properties of the XOR. This is a different solution. I don't think you need you don't even need 0 here because it won't be empty. So if you don't provide an initial value to the reduce function, then you cannot pass an empty iterable. But here we shouldn't need it. Yeah, that's it. So yeah, this is a little shorter, I guess. And both our solutions are linear. So the size of the array could be much bigger, could be 10 to the 5, and this would work. I guess another if you want to avoid using set, I mean in LeetCode it's okay to use sets, but in other contexts it can be hacked. So you could use something like this. You group by, you sort, then you group by all the consecutive elements, and then you keep only only the value for each group. And this is another way of doing the unique, getting the unique values in Python. All right. Let's move on to Q2. Find occurrences of an element in an array. You are given an integer array nums, an integer array queries, and an integer x. For each query I, you need to find the index of the queries ith occurrence of x in the nums array. If there are fewer than queries of I occurrences of x, the answer should be -1 for that query. Return an integer array answer containing the answers to all queries. Okay, so this one is pretty, for a Q2, I think for a medium, I think it was kind of too easy. I mean, the size of the array and the queries is 10 to the 5, but so the first observation is to realize that you don't even care about the array. I mean, you only care about the positions where x occurs, right? So if there's any other element that is not x, then you can ignore it. So you can start by going over all the the elements, and if the element is x, then you just save that index. Okay, so now we have all the indices where x occurs. So now we can answer the queries, and this is going to be well, in queries, and we want to, yeah, I guess we could do it as a one-liner. So here, if I is less than or equal to the number of indices, so I is one base, that's why I'm using less than or equal. So I want the ith minus 1 position, and else I want minus 1. And this should be all there is to it. All right. 1 second. Why does this take 1 second to execute? That's kind of weird. Is that repeatable? Yep. I would expect this to run pretty fast. Well, I guess it depends on the number of test cases that they have. Anyway, so okay, so what can we take away from this problem? I mean, it's pretty straightforward, but so one thing, I actually I misinterpreted the problem. I didn't realize that x was an input, and I thought x would be part of the query. And that makes it a little more interesting, because here, instead of having the list of indices for x, we would have the list of indices for all the values. So we could have so a typical code pattern is to use like we would have idx be a default dict, and we would have a list for each of the values, and then here we would do something. We would access this dictionary for the given value for the query, and then we would access with the index. So I guess that would have been a better problem. Still pretty easy, to be honest. But so another variation that you could have, instead of asking for the kth position, you could have the query giving you a position. Not so notice here that we're given the position not in the original array, right? But the number of occurrence, right? So I guess a variation of this problem would be to give you like the next occurrence of x. And in that case, you would use something very similar. You would also have a list with all the occurrences, but instead of just returning the index, you would do a binary search to find the next occurrence. So yes, I'm trying to think about ways to make this problem more interesting, because there's not much to say about the actual problem, I think. So yeah, all right. Yeah, also I recommend you, so one thing that you should do when you practice LeetCode, you want to get as much as you can. So everyone tells you that you have to solve problems to get good at LeetCode, and that's true, but it's not the entire truth. I think it's not just mindlessly solving problems. You have to get the most of each problem that you solve. And one thing that is usually good is to try to generalize the problem, to try to think about how you could change the problem and see if maybe the solution still holds for variations of the problem, or you can think about ways that you could change it, maybe change the constraints. That's usually a good way to learn more than just the actual problem that you're getting. Anyways, so Q3, find the number of distinct colors among the balls. You're given an integer limit and a 2D array queries of size n times 2. There are limit plus 1 balls of distinct labels in the range from 0 to limit inclusive. Initially, all balls are uncolored. For every query in queries that is of the form XY, you mark ball X with the color Y. After each query, you need to find the number of distinct colors among the balls. Return. First time I read this problem, I thought it meant only colors that appear once. Yeah, distinct usually means that, yeah, if they occur more than once, you counted only once. Return an array result of length n, where result, by the way, welcome obis, denotes the number of distinct colors after the ith query. Note that answering a query, lack of color will not be considered a color. Okay, so here, okay, so the limit is large. I had to stop and think what the problem is even asking. Yeah, I mean, you're just coloring these positions or balls if you want. I mean, this doesn't matter that they are balls. That's just a red herring. So you have numbers from 0 to this 10 to the 9 up to 10 to the 9, right? And they are initially uncolored, and you have to you get instructions to change the color, to paint of a new color, and you have to keep track of how many distinct colors there are. Okay, so yeah, so here you could say, okay, I'm gonna counter, reverse counter. Okay, don't spoil it yet. Okay, so here you could say, okay, I want to simulate this. I want to keep track of the color of each position. Okay, but there are a lot of positions, right? There are 10 to the 9 plus 1 positions at most. So that's out of the question. You cannot keep track. You cannot have an array of all of them. But that's actually misleading, because you're only going to paint as many, at most, as many as there are queries, right? And the number of queries is 10 to the 5. So at any given time, you're going to have at most 10 to the 5 colored cells. So we could use we could have a dictionary that determines the color, that stores the color of each position, right? And we know that the size is going to be reasonable. And then whenever you have to know how many distinct values, you can use a counter. So we could use a counter of the colors, the distinct colors. Okay. So now we go over the queries. So we have an index and we have a color, right? And we want to know, so we want to unpaint this position, right? Because we're going to color it now of this new color. I mean, it could be the same, but it doesn't matter. So first we uncolor it, and that, what does that mean? So if I is in color, we want to remove from the counts, we want to remove this color, one occurrence of this color. This remove is something that I usually do. I like to have a special function, because when you subtract 1 from a counter and you get to 0, it keeps the key with a 0 value. So if you want to know how many distinct values there are, you're gonna count that one that has 0 occurrences, so that you don't want that. So I usually create this function to do a proper remove, right? And I want to have that encapsulated, so that I don't have to think about this detail in my code. So here we want the new color to have 1 more occurrence, and the color of I now is going to be C. It doesn't matter if it wasn't color before, or if it was and it changed, or if it was color of the same color. It doesn't matter. Now we set it to C, and we append the length of the colors, right? These are the same colors. And we have to create this. Okay. And this is it. It's pretty straightforward as well. Why they all take 1.2 milliseconds? That is a lot. I think this is pretty optimal. Well, I guess, well, we could talk about the how optimal this is. But yeah, I don't think you could. I don't think I could do this better, faster. So the colors, what's the range of the colors? Oh, it's also 10 to the 9, yeah. Your solution, I'm not gonna look at it right now, but if anyone's interested, do you think it's simpler or faster? All right. So maybe more memory efficient. Like you don't have this 2 data structures. Yeah, but those stats, I don't even look at the memory stats. Like, do you have the two data structures or not? Um, yes. Okay, then it's should be the same then. Anyway, so yeah, I guess you do index compression or something like that to avoid. So lately I've been thinking of ways of avoiding using dictionaries in Python because sometimes they are slow. But I guess in this case it would be a hassle to do it. It's not worth it. Well, I mean, in LeetCode, it's usually not worth it. All right, so let's move on to Q4. Block placement queries. There exists an infinite number line with its origin at 0 and extending towards the positive x-axis. You are given a 2D array queries which contains two types of queries. For a query of type 1, which has a parameter called x, build an obstacle at distance x from the origin. It is guaranteed that there is no obstacle at distance x when the query is asked. For a query of type 2, we have two parameters, an x and a size. Check if it is possible to place a block of size anywhere in the range from 0 to x inclusive on the line, such that the block entirely lies on the range. Okay. A block cannot be placed if it intersects with any obstacle, but it may touch it. Note that you do not actually place the block. Queries are separate. Return a Boolean array results where each is true if you can place false otherwise. All right. So here we have a diagram. And yeah, and even though they say it's infinite, but the maximum x, which is the range, you care about the range from 0 to the maximum x, and that is limited by 5, 10 to the 4 times 5, so 50,000. At least one query of type 2, okay. Yeah, otherwise it's an empty result, I guess. Okay, so let's think about it. So we have the, why are those constraints so sus? Oh, yeah, I don't understand why they made this. I don't understand this. So I do understand why they make this range relatively small and not 10 to the 9, for example. But I don't understand why they make this limited by the size of the, it's like the number of queries, 3 times the number of queries. That makes no sense to me. Anyways, so do any of you know why that limit? So we have a line that goes to infinity, but we can say so it's limited by 50k or so. So this is 0, 1, 2, 3, and so on. But we can think about segment as we have a segment initially that starts at 0 and goes, let's say it ends at the end, right? So we know that this is a free segment, right? We could place a block here. Well, I mean, it's not really we could place a segment here in any place, right? And then we're gonna get queries for placing. So let's say that we get a query of type 1, and we get 3 as x, right? So we're placing now an obstacle here. So now we can think, we can break down our segments into 2. Now we have one that starts here and ends here, and another one that starts here and ends here, right? And we have to, if we want to place a block, we would have to place it in one or the other, right? We cannot place it. And then we get another query. We get another query here. Let's say that this is 15. And so now, so notice that when we break down a segment into 2, we need to figure out in which segment this obstacle is located. So it's located in the segment that starts at 3, right? And so the segment that starts at 3 was length of this whole thing, but now it will end at here, and we will add a new segment that starts at 15 and ends at the end, right? So that's how we can handle these queries, right? The queries of type 1. We keep track of the places where the segments are, and we find the segment that contains the given obstacle, and we break it down into 2. And once we have that, then notice that we want to make, so if we get a query of, I don't know, we get a query of type 2 that has x is 16, and then size is 2. So that means that we can place a block. We cannot place a block in 16 or in hey, Chandu16, welcome. So we can at most place the block at 14 or less, right? Because the size has to be 2, right? So we have to leave this buffer. And so we want to know if in this range here, in the range from 0 to 14, we want to know if there is a segment of length could I know what you're thinking? Of length greater than or equal to 2, right? If we find any segment that is located in this range, the range from 0 to 14, and its length is at least 2, then we can place our block of size 2. Right, so this is what's called a range query, right? We're asking for the maximum. We want to know whether the maximum segment length, right? To know if there is a segment, we can just check the maximum and check if it is greater than or equal to 2, right? So we want max range queries this is something that we need. And then the other thing that we needed was to find out where the segment starts that contains an obstacle. And for that, we could use a sorted list. And we can use the bisect. We can use the bisect method to find the segment that contains the obstacle. So we only had to keep track of in the sorted lists of the start of each segment, and in our and to respond, we will use segment tree, and we have to keep track of where it starts, where the segment starts, and what the size of that segment is, so that we can get the maximum. Okay, so with all this, we're ready to code. I'm not gonna go over the segment tree. I've done it before, but today I'm gonna skip it. I mean, you can find, I have a video in YouTube where I explain segment trees from scratch, so you're welcome to look into that. But here, yes, I have a segment tree that we could set any value at a bit. Remember that the interface of a segment tree is just an array that we can set a value, and then we can ask for the maximum in a range, and it's going to do it fast. It's going to do it in logarithmic time. Okay, so, and let's say, so segment trees like powers of 2s, and the smallest powers of 2 that is greater than the size of this thing of 50,000 is 10 to the 16, which is 64K, as you should know. So we can use that as the size. So we can have how do we, yeah, let's call this start, and we create a sorted list, and initially we have the start, we have only one segment that starts at 0, right? And then we want the size of the segment that starts at each position, that is going to be a segment tree of size n, and we want to set at 0 we have a segment of size n. Okay, so now we're ready to answer the queries. So we have queries of type 1 or otherwise type 2. And let's do type 2 first, which is a little bit easier. So here we just want the maximum size from 0 to x minus the size, right? Because remember that we had to leave that space for the, and we want this to be greater than or equal to the size, right? If we find any segment that starts in this range that has size greater than or equal to size, then we found we can place the block. Okay, and here we have to find, first we have to find the start of the segment that contains the obstacle. So we can use bisect, right? I mean, it doesn't matter which one. I mean, the obstacle cannot be a start of a segment, right? Because the obstacles are never, so initially we have a segment that starts at 0, and then all the segments that we add start at an obstacle. So none of those are valid for the following obstacles. So it doesn't really matter if we use bisect right or bisect left, but we want the previous element, because this is going to give us the element that is greater. The position that bisect is going to give us is the position that is greater, but we want the one that is less than it, the largest that is less than it, because that's the one that is going to contain x. Okay, so now we have our y, let's call it y, which is the start of this. So yeah, I guess we don't even need to name that. So this is going to be the start of the segment that we want to split into 2. And we know the size of the segment that starts at I is going to be, yeah, this is kind of weird how we write this, but this is just a get. This is just a get, right? Because we're doing the max of one element only. And so I guess we could let me yeah, to make it prettier. Can we talk about percentage a bit? I don't follow. Couple of questions. Purpose of sorted list. How is a segment tree producing the max length of all the segments? So we place division modulo stuff. So smart coder. So we're creating a segment tree that has at the beginning of each segment, right? If we have a segment that starts at 3, then we place, and it has some size, then we place that size at position 3 in the segment tree. So then when we make the range query, we're gonna get the maximum size of all the segments that start in this range, inclusive. Okay, so now we have to remove from start, right? We want to remove this one. Well, I guess we don't need to. Yeah, we don't need to remove this because we're gonna have a start at I, right? So we only need to now set the size. We have to change the size of the segment that starts at I, right? Because now it's going to be x minus y, right? X is where we put the obstacle, Y is where we are adding, where a segment starts, right? So this is the new size of the first segment. And then we want to add a new start, which is going to be the obstacle, right? Where we put the obstacle, we're gonna start the second part of the segment that we split, and so we have to set from X, and now the size is going to be N, which was the size of the original, minus the size of the first part, right? Which is X minus Y, and this is it. So purpose of sorted list. So the purpose, yeah, I call this size. So so the sorted list has all the starting points of the segments that are free. And since we have all the operations that we need to find the segment that contains the obstacle, right? So that's why we use this bisect, which is going to give us pretty quickly where the segment that contains the obstacles starts. And then we also want to add the new segment, right? When we split it into 2, we want a new segment to start at the obstacle. So we use these 2 operations, the bisect and the add. Both had to be fast for this to work. Can you explain your sec tree solution using example? The explanation is not very intuitive. Example 2. So here at the beginning, yes, please. Sergio, welcome. So here at the beginning, we're placing an obstacle at 7, right? So here it is. And then in the third query, we place an obstacle on 2, and those are the only obstacles. And so here, so the first query is true because we only have this obstacle here. And so here, right, it is true. Do you understand why it is true here? So we have an obstacle at 7, and we want to place a block of size 6 in the range from 0 to 7. So of course we can. Maybe you can use the... Okay. Well, this is tilted. What the hell? Anyways, so first, so here the largest x. So here they have up to 8. Okay, let's do it up to 8. So we have 0, and let's say this is 8, 7, 6, 5. Okay, so first we place an obstacle at 7, right? So we place an obstacle here, and so we had a segment. Let's say that it ended at 8, right? We had only one segment at the beginning, but now we found the segment that contains the obstacle 7 starts at 0, right? So now we have to break this down into 2. So we break it down into a segment that starts at 0 and has size 7, and then a segment that starts at the obstacle starts at 7 and goes up to 8. So we have these 2 segments, right? And in our segment tree, remember that the segment tree is just an array. Functionally, it's just an array. So we now have a segment that starts at 0 and has size 7. And we have a segment that starts at 7 and has size 1. But it's an array of size 2n. 2 to the n, you mean? Yeah, I mean, it doesn't matter the size. It's a size that is bigger than all the x's. I just chose a power of 2, but it doesn't need to be a power of 2. So here it's just 8. Okay, so at this point we have this in our segment tree, right? And zeros in all the other positions because we don't have any segments starting at those positions, right? So now we have to solve this query, right? So here x is 7 and size is 6, right? So we say, okay, what's the maximum? What's the maximum in the range? The maximum. Hey, Xproofs, welcome. What's the maximum from 0 to x minus 6, right? So it's 1. So the maximum in these two places, this is equal to 7, which is greater than or equal to 6. So that means that the query is true. Let me finish this. Okay, so this is how smart coder, are you following? So this is why we answer true for this query, right? Okay, so here is true. This is our data structures are the reason you can place a block of size 6 in the range is because the query that adds the obstacle at 2 occurs afterwards. Yeah, this is in order, right? Yeah, one thing. Yeah, the obstacles. So here now we add I'm still unsure what the secretary is answering. So the secretary tells us that there is a segment that starts at 0, a segment that is free that starts at 0 and has size 7. So that means that we can place, if we have 6 we have 7 places and we want to place a block of size 6, so we can. Well, maybe let me continue with this and maybe you'll see why it makes sense. So now we have this query, right? We have the query that we add a new obstacle. So we add an obstacle at 2. So right here, right? So we look in our sorted list and we find the largest start of a segment that is less than 2, which is this one, right? It's 0. And so we add a new segment that starts here, right? It starts at 2 at the right at the obstacle, and now we change this. Now now we want to change this, right? Because now we have a segment of size 2 here. But now we have another segment, one that starts at 2. And it has size 5. So that's how we change our segment tree. Right? And now we want to answer this query. So what do? We ask for the maximum in the segment tree. So the maximum size from 0 to so here x equals 7 and size equals 5. So we want x minus 5, right? It has to start, it cannot start after that because then it wouldn't, the size will surpass 7. right? So we want 2. So now, let's say we have a large segment, 1, 5, and smaller segment. Next obstacle occurs at 10. So now we have segments 1, 5, we're not changing the large segment. Yes. So what is your question in that case? Okay, so now our query is going to is asking for this range, right? 0, 1, and 2. And the answer is 5. Which is greater than or equal to 5, so this query is true. But now we have the same what the hell? Okay, so now the range is going to be from 0 to 7 minus 6, which is 1. And the longest segment here is going to be of size 2, right? But 2 is not greater than or equal to 6, so this is false. Can you, smart coder, can you explain the point of that case that you are describing? Did I submit this or not yet? All right. 5 seconds. That's okay, I guess. I am lost, but what? So I'm explaining what. So when I say so these segments are the maximal segments. I don't know what we are storing in the sec tree. What we're using the sort. How are the ranges impacted and how the sec tree. So what we are storing is what I said here at the beginning. So, whoa. We have maximal segments around all the obstacles, right? So initially we have only one segment that covers the whole thing. Then when we add an obstacle, we split it into 2 at that obstacle. So we have now another segment that starts at the obstacle, and the segment now ends at the obstacle. Is the segment tree mandatory here? Yes, because we need range queries. We're asking. We need range queries. So that's what's. So these segments are what we conceptually what we have, and we are going to represent them in these 2 data structures. The sorted list is going to have the beginning, the start of each of these segments, And the segment tree is going to have the size of each of the segments at the beginning, at the start of each of the segments. So we just have segments and we have them represented in these two data structures so that we can make all these queries that we are interested in. Holy fuck, now it makes sense. Okay. So we use a sorted list because we want to find quickly the segment that contains the current obstacle, so that then we add a new, and we want to add a new segment, a new start of a segment at the right. So here we add a new segment that starts at the obstacle, and we make this segment now shorter. The segment that starts at I, at Y, now goes up to X, right? So the length is X minus I minus Y, and then the other segment is just whatever is left, right? The area that is covered by the segments is always the whole thing, right? Because we're only splitting them, but the area that they the length that they cover in total is always the whole thing. Okay. We have to take for splitting. Well, not +1. We are only, so we don't care about the next segment. We leave the next segment alone. We just add a new. So this is the only thing that we need, which is so it doesn't matter if we use bisect left or bisect right, because X is not going to be part of the, is not going to be in start, and so we're gonna bisect is going to give us the position of the smallest element that is greater than or equal to X, but that's going to be the next element because it's greater than X. We want the one that is that it starts before X. That's why we subtract 1, and we know that there's always 1 because we always have a segment that starts at 0, and X is greater than 0. Okay, it's always greater than 0. So that's why we don't need to check any bounds. We can just access, which makes sense, right? Because we're covering with the segments, we're covering the whole thing. So whatever the location of the obstacle is, there is one segment that contains it. So the code, I think, is pretty simple. I mean, you need to have the template of the segment tree, but once you've done that, once you have that, the code is pretty straightforward. I think this was a nice problem. Not too hard, but it was the right difficulty. I don't think you had, like in some contests, you didn't have anyone who solved the whole thing in 5 minutes or something crazy like that. If we're placing X, then at X new value, Yeah, I know it's hard. I mean, I'm not saying it's not hard. It's a hard, but it's not one of the hardest. But I haven't seen the stats. That's interesting. But yeah, I think probably 400 is standard for Q4, right? I don't know. Isn't it kind of the mean to have like all 500-ish subs? I mean, it was a little tricky to get this right. Usually you have to pay attention to all the off by one errors. All right. So that's all I have. Oh, it's been pretty 1 hour and 15 minutes. That's more than I expected. I guess we went over pretty in depth. So that's good. So thank you guys for watching. Hopefully tomorrow I'm gonna be doing a stream for the weekly, for tonight's weekly. So stay tuned, and thank you very much for your support. Bye bye. Thanks. Thank you, Smart Coder, for the questions and for keeping me, for making me clarify. I appreciate it. Bye bye.